Okay, so here we're going to see some class notes for total internal reflection. So what you want to do is open up Notability and have that open in the background on your iPad so that you can take notes in your refraction class notes. So this is total internal reflection. Here is an awesome picture of Michael Phelps, and what you can see is that the camera is under the water of the pool. And you can see that it's looking up at him from the bottom, but you can see his reflection on the top side of the water from underneath. And that's exactly what we're going to be taking a look at. Here's another picture. This is a turtle under the water, and you can see the reflection of that turtle on the surface of the water. So what is this total internal reflection? In your notes, you probably want to copy this. You can maybe screenshot this screen if you want, or draw this picture out in your notes and take a look. In the half circle that you're taking a look at, there is water, and there is a beam of light moving from water into air. And if you take a look at the very first image there, it says refraction. You can see you're going from slow to fast, from water to air, and the light refracts in that image number 1. In image number 2 there, you can see that the light beam has reached what's called a critical angle. So if you get that beam to get just to the right angle, and it depends on the material, in this case we're looking at water, but at just that perfect angle, the light will no longer leave the water. It's going to skim perfectly at 90 degrees from the normal. So it's going to go straight across that boundary between the water and the air. And eventually, if you keep increasing that angle more and more, that incident angle away from the normal, it will no longer skim across the top of that boundary between the water and the air. It will actually reflect underneath. And maybe you've had that experience where you have seen this, where you've been in the pool and you've looked up to try to find your friend, outside on the deck. And if you gaze a little bit further, you can actually see the floor of the pool above you when you are underwater. And that's what's happening. It's called total internal reflection, because that's exactly what's happening. The light is reflecting off the top surface of that water because it can no longer leave that material and refract as it goes. Here's another little image for you to take a look at. It's a little bit blurry, but you can see it, I'm sure, on your screen. You can see in this case, we're going from glass to air, so very much the same as what we just looked at. You might want to pause the video here for a moment and jot down a couple of key things. For example, when the angle is equal to the critical angle, the light will refract at 90 degrees. It's going to skim right across that boundary, which is the middle picture that you're looking at. You can see on the left there, if the angle of incidence is less than the critical angle, the light refracts away from the normal. If it is equal to the critical angle, it refracts at 90 degrees. And if it's greater than the critical angle, it will reflect back down inside that same material. So I highly suggest writing down those 3 things. There will definitely be a question on the assessment regarding that the exact phrases here that you've just looked at. I want to know if you understand what happens if the angle is less than the critical angle, what happens if it equals the critical angle, and what happens if it's greater than the critical angle for 2 materials. So make sure you put that in your notes. Again, here is just another image for you to take a look at. It's from glass into air. And we'll start by taking a look at the green ray of light that's coming out. That one refracts. The red one is at the critical angle. The blue one is total internal reflection. It actually reflects. And don't forget, when things reflect, what law is it that they follow? Follows the law of reflection every time. So the incident angle will equal the reflected angle within that material. One other thing that's interesting that I want you to put down in your notes is that as that angle increases, the refracted ray becomes more and more dim. So if you take a look here, you can see I've got different angles. There's a laser underwater. It is refracting out into the air until it reaches the critical angle and reflects back within the water. But if you take a look going from 0 to 15 degrees to 30 degrees, 45 and 60, as your angle increases more and more, the intensity of that beam refracting out into the air is less and less. The light actually gets dimmer, but the reflected ray becomes brighter. And so you can see the words underneath there. You want to make sure that you have this, indicated in your notes as well. So kind of the big ideas here you want to make sure you have written down. For total internal reflection, that's when the light is no longer able to refract. It's when light is going from a slow material to a fast material, so more dense material to a less dense material. The light is just past the critical angle of 90 degrees so that it reflects back on the inside, and when it does reflect, it follows the law of reflection. This is the worksheet we're going to be working on that you should be able to answer after having taken some notes and doing the reading in your iBook. Okay, what you can see here is a video of a demonstration of total internal reflection. So what has happened is there's a 2-liter bottle full of water, and they poked a hole in the side of it, and they're shining a green laser through it. And the laser is totally internally reflecting within that little stream of water. So it looks pretty cool there. And this next little video is meant to be a joke of a woman who clearly never took physics class. So view and enjoy.
Hi, today is July 6th, 2007, about 4:30 p.m. I'm just wondering what the heck is in our water supply, what the heck is in our oxygen supply of the metallic oxide salts that create a rainbow effect in a sprinkler. What is oozing out of our ground that allows this type of effect to happen? Not just around our sun and our moon anymore, everywhere we look. The visible spectrum is rainbows. This cannot be natural. We all know it wasn't something that happened 20 years ago, but now it's happening now. We as a nation have got to ask ourselves, what the hell is going on? What is oozing out of our ground?
So do you know why there was a rainbow coming out of her hose? If not, you need to do a little bit more reading right about now and see if you can answer that question for class tomorrow.